Okay, so we're back at linear algebra. How fun. And I'll remind you that we did last lesson, we did a review session, and now we continue with the material. We've finished. I'll open the math wiki to see the general syllabus. We've finished vector spaces and we're about to start linear transformation, linear functions now. And just a quick review of what we learned so far. So the first chapter was fields, and specifically we learned about the complex numbers field. Then we did linear system of equations and how to solve them using matrices. Then we studied about algebra of matrices, mainly multiplication of matrices, inverse matrices. Then we did vector spaces and subspaces. We defined what a vector space is, and we said that a vector subspace is a subset, which is also a vector space with regard to the same operations. We learned about linear dependency and span, and dimension, of course. And we learned about the spaces of a matrix. That's that, I think. I think it's here. Just a second. Remember, there is a headline for it. Here, yes. So we'll learn about the row space and the column space and the null space and how to find them, and that's that. And now we're on to the last chapter, which is good because we have only 2 sessions, this session and next week. And we study about linear transformations. Okay. And if you have any questions or notes, you're welcome to it. So, linear transformations. First, note that transformations are simply functions. So the name is a bit misleading, and sometimes students forget at first that we are speaking about functions, but not all functions. A special set of functions, which we call linear functions. Main purpose, I don't know if it's a main purpose, I will write it. Main purpose, and prove that the linear functions between finitely generated spaces are exactly the matrices. With a small but important, with a small yet important translation between the two. And so that's like one of the main things you should learn in linear algebra 1 in general. I just scrolled the file a bit before I started the class, and I looked at the first page. And remember, other than saying hello, the main purpose, wow, it's even the same thing. I didn't notice. And the main purpose of linear algebra is to study linear functions. And I didn't say at that point that the matrices are the linear functions, but I'm sure I said it sometimes. But I said the main purpose. That's okay. So without further ado, because we talked about it a lot, I'll go straight to the definition. Given two vector spaces, V and W, over the same field F, so the scalars come from the same place, but the vectors could be different. There could be, the vector spaces could be R squared and R fourth, or and like the vector space of sounds, like I said, the functions. So we have two vector spaces over the same scalar field. A function t from V to W, and a function, you should know what the definition of a function is from discrete mathematics. So a function t is called a linear function or linear transformation if the following two holds. For every V1 and V2 in V, it is true that T of V1 plus V2 equals to T of V1 plus T of V2. Second, for all A from the field and for all V from the vector space, for every scalar and every vector, it is true that T of AV equals A T of V. So any function that follows these two axioms or rules is called a linear function. And what is the domain and what is the range of this function? Simply put, this function, what goes in and what goes out to this function?
It's BB.
What?
It's from B to B, or?
It's from B to W.
Okay.
So again, what comes in and what comes out in a single word? What type of things are within the sets, these sets?
Are they matrices? I mean, it's vectors. Yeah.
Vectors, exactly. That's what I was looking. That is what I was looking for. Linear function is a function that gets vectors and produce vectors, and the following two conditions hold. Okay, so that is a linear function. When you studied function in calculus, I'm not sure who's your lecturer. When you study functions in calculus, you usually study them by their graph or using their graph, the graph of the function. Here, you never, or almost never, study this function using graph. Why? Because assume that the vector space is at least two-dimensional, then the domain is two-dimensional, and the range is at least two-dimensional. So what will be the dimension of the graph? At least.
You mean, again, what's two-dimensional? Both.
Assume that both V and W are at least two-dimensional. V is at least a plane and W is at least a plane. So the graph of the function, how many dimensions will it have?
At least 3.
At least 4. At least 4. Because the graph is built from pairs, a member of the domain and a member of the range, which is sent to. So if I have two vectors, each of them from a two-dimensional space, then altogether we get at least a four-dimensional space. And that's why we can't see the graph. Okay? We don't know how to visualize four-dimensional things, not to talk about above. So our way to discuss functions here will be very different in calculus. We cannot see the graph at all. But like I said, every function is actually a matrix, and that's the way we'll look at them. So and we'll see in a while how does that look. Any questions up until now? I didn't give it even one example yet.
I'm sorry, about dimensions of a graph. You mean because B and W are different vector spaces, then each dimension of each is one dimension on the graph, even if they are the same one?
Yeah, because they're not the same one. Yeah, it's like saying the same one is like drawing the x-axis and the y-axis on the same axis. It doesn't make sense, you see?
No, yes, I mean
That's why they must be different on the graph. Even if it was from the very same vector space to itself, you still on the graph need to draw it twice, because on the axis of V, you mark the vector of V, and on the axis of W, you mark the T of V, the image of V. And altogether, you need at least 4, unless one of them is one-dimensional, and then you can actually draw it. Okay. But that's the exception, right? Usually it's a high dimension, and we cannot imagine the graph. That's the problem with linear functions. The way we imagine them are matrices. That's the only way. Okay. Just before I will give you the first example, does this rule remind you of something?
Yeah, it's just matrix algebra, right?
Exactly. It's the distribution law. And the rules of being a linear, and this is also matrix algebra. So the rules of being linear functions are identical to the rules that are true for matrix algebra, like Thomas said, and that's a hint as to why the two are the same. It's not a proof because it's not all the rules, but the rest follows. And it's easy to think about it as multiplication. So notice that these rules are similar to matrix algebra. Not surprising. Therefore, we note as a shorthand, instead of T of V, we write it as multiplication. We write TV. Okay, so it's a bit confusing because you would never write a function this way, right? You never write yx instead of y of x. But in linear functions, we do. We write TV for short. And the reason is, and you'll see it in linear algebra 2 as well, is that as mathematicians, there is not there isn't any difference between almost any difference between matrices and linear functions. So we really regard it as multiplication, and all the rules apply as well, so it makes sense. Okay, let's do a first example. Consider the function t from r cubed to r squared. So this function gets the input, the domain is vectors from the three-dimensional space, and the output are vectors from the two-dimensional space. And I need a formula such that t of x, y, z is x plus 1, y plus z. Do you suppose this is a linear function or linear transformation? It's the same. I wrote is twice. Is t a linear function? Do you care to guess or give me a, I don't know, full answer? Sammy is shaking his head. Look at the road,
yes.
Sammy, not at the notebook. Thomas says yes, Sammy says no. One of you is correct. Okay.
Definitely. It's can it be a 3x2 matrix and
Let's leave the matrices for now. We will have time for them in the near future. Let's try to look at the rules just as an example. So choose rule 1 or rule 2. We're just trying stuff. Thomas, rule 1 or rule 2? Choose randomly.
2.
Okay, I can't determine if your choice was random or not. Okay, now choose random vector and a scalar. So the vector ought to be from r cubed, right? So choose a random vector from r cubed.
1, 2, 3.
1, 2, 3. Choose a random scalar.
2.
2, great. And let's check what is t of v. So t of v is x plus 1 is 2 and y plus z is 5. Do you agree?
Yes.
Okay. Now, what is t of 2v? That's what we have in the rule here, right? So if I do the multiplication within the parenthesis, sorry, so 2v is 2, 4, 6, right?
Oh.
And what does that equal to?
3, 10.
Exactly. What is 2 times t of v?
It will give 410. Yeah.
Which is different. So t of 2v does not equal 2 times t of v, and therefore, a nice view, Sammy. It's better than your armpits, which was the view before. And poor Sammy is gonna need therapy after the course with me. He kept battering me. Okay, sorry. But you were right, Sammy. So I'm allowing myself. T is not a linear function. Okay, it looks almost linear because all you have is variables under addition, but the so-called non-homogeneous element here ruins it. In general, that would be our first proposition. If T from double from V to W is a linear transformation, then T of the zero vector must be the zero vector. So the zero vector must be sent to the zero vector. And before I'll do a proof, I'll give you an example. With the above function, T of x, y, z equals x plus 1, y plus z, what is T of the zero vector?
It's 0, 0, right? No, 0, 1, 0.
It's 1, 0, which is different than 0, 0. And again, this is not a linear transformation. Okay? And now, proof of the proposition goes as follows. T of 0, there are a lot of zeros in this proof, so you need to follow carefully. T of 0 equals to T of 0 times 0, where the first 0 is the 0 of the field, and the second 0 is the 0 of the vector space. Since the 0 scalar times any vector equals to the 0 vector. Now, from the rules of linear transformation, what can we do with that scalar here?
What can we do?
Take it out.
Exactly, we can take it out or move it to the left, however you wish to think about it. So we can take it out. So it's the 0 vector times T of 0v. And what is 0 scalar? Sorry. And what is the 0 scalar times any vector?
0.
The 0 vector, right? But of which vector space?
R2?
But in general, I mean W.
Oh.
And why are we sure? Because that happens in W. After we applied T, we are within the range of the function, not the domain, right? So T of 0v is definitely a vector within W, and the multiplication here is within W. And so the 0 is 0 of W. So altogether, we obtain the result that the 0 vector is always sent to the 0 vector. One is the 0 of the domain, and the other is the 0 of the range. Every time that I'm saying the range, I'm thinking about becoming insane. Okay. Any questions so far?
Why does thinking about the range make you become insane?
Can anyone answer Sammy? Did anyone understand my joke? That's my question.
Thinking about the range makes you insane.
Yeah, deranged.
Deranged.
Oh, I see. Play on words. Haha. Good one.
Yeah, it's a thank you.
Funny.
Okay. Fine. Now, an interesting example. Say V is the vector space of all differentiable functions, all functions that have a derivative, and W and the vector space of all functions. And these two are not finitely generated, so we don't talk about them much. Okay, but still it's a very important example. So define the function t that gets any differentiable function, and its output, can you guess where would the functions, would t send a general function? The domain is functions, the range is functions, right? So I need for you to tell me what is the so-called formula, what is the method on which we send functions from the domain, we match functions between the domain and the range.
You make it incontinuous?
The hint is within V. V is the space of all differentiable functions. So what does each differentiable function has?
A derivative, so you derive it.
Exactly, to the derivative. Okay, so it's a bit confusing because it's a function that sends functions to functions. But first of all, you learn discrete math and you saw stuff like that. And secondly, that's one of the things about linear functions in general in this course. We don't just send number to numbers, we send vectors to vectors. So functions are just a type of vectors. Okay, and my question is T a linear transformation?
Can I ask a question first?
Of course.
I don't understand this function. Like I don't understand why is it that t of f equals the derivative of f?
No, that's the definition. I defined the function.
Oh, okay.
I defined some function, right? That's an example. And I'm asking whether the function that I defined is a linear transformation or not. It is a function between two vector spaces over the same field, the real field, right? It's a made-up function which I gave as an example. It is obviously an important one, right? But for the sake of argument, it's just an example. I invented it. My question is only whether this is a linear transformation or just a function between two vector spaces.
We can try to multiply it by something, right? Or
what is your guess?
I guess it is.
So let's see the two rules. What is the functions of the sum of two vectors? What is t of f plus g? So by definition, it's the derivative of f plus g. Do you agree?
Yeah.
from calculus, but even high school calculus. What is the derivative of f plus g?
The sum of the derivatives.
Yeah, it's the derivative of g plus the derivative of f, which is t of f plus t of g. Agreed?
Yeah.
So the first rule applies. What is the function of c times f? It's the derivatives of the scalar c times the function f. By rules of calculus, what happens to the scalar? It comes out. It's c times f prime, which is c times t of f. So yes, indeed. Okay, that is an important linear transformation. אני אשמח לשתייה, כן. Transformation. Okay. Sadly, I'm not sure that I will have to time to show you why this linear function is so dramatically helpful. If we'll have some spare times, maybe I will, if you remind me. But that's just an example. Now, let's look at the same function, but over the finitely generated spaces of polynomials up to degree 2. Okay. So R2x is the set of all polynomials up to degree 2. Why do I say up to and not exactly of degree 2? Can anyone say?
Because they may not have x squared in their sum.
Why? But I wrote x squared here. So how come it won't be there? In which case?
Is equals 0.
Exactly. Because the coefficients might be 0, then the degree might be lower. Okay? That is a vector space. Now, look at the function t. From this vector space to itself, that sends each polynomial to its derivative.
Sorry, Erez, one question.
Yes.
What makes the polynomials up to degree 2 finitely generated?
They are the span of 1x and x squared.
Because the amount of vectors is finite.
Right? This is a span. This is actually a span, right?
Yeah.
Yes, finitely generated, meaning that in the in a set that spans the entire vector space, there is a finite. There exists a set with a finite set that spans the entire vector space. Even if I didn't cap the degree, it won't be finitely generated. But again, there's a dimension here even. What is the dimension of R squared? Not R squared, sorry, R2x. What is the dimension of this space?
3.
3, exactly. Because we need 3 vectors to create it. The constant 1, the function x, and the function x squared. Okay. So it is finitely generated, and you'll see why that is important for me. But I'm just saying that T of A plus Bx plus Cx squared, what does it equal to?
The 0 plus the derivative of bx plus the derivative of cx squared.
Yeah, so what is the derivative?
Oh,
Plus 2cx.
B plus 2cx, right? And now my question is, could the function t be applied by multiplying with a certain matrix? What are your thoughts? Could there be a matrix that derives the polynomials?
I mean, obviously, yes. If you already told us that it's a linear transformation, but which one? I don't know.
Great answer, Thomas. You're 100% correct. Assuming that I didn't lie to you, then the answer is yes. But we will see together why it makes sense. So the problem is a problem of translation. So obviously I could not multiply a matrix. I could not multiply a matrix with a polynomial, right? Because that is just silly, right? I'll write that. First, we cannot multiply a matrix by a vector, right? But, however, who can tell me which vector I can take instead of the polynomial?
Transpose?
Not exactly a transpose, because this is not, it's not a matrix, right?
Mhm.
But when you said transpose, what is the column you were thinking about?
The column I was thinking of, the first one, or like what?
Yeah, when you say transpose, you thought of a column, right?
Mm-hmm.
Tell me the elements of this column that you had in your head.
ABC.
Exactly. So you're correct. It's just not transpose. It's the coefficients. It is important, but it's the coefficients. We can multiply a matrix by the coefficients of the polynomial. Meaning I can take a matrix and multiply it, like Thomas said exactly, by the A, B, C. Agreed?
Yeah.
And what do we wish to obtain in the image? I got the domain was, the vector from the domain was A, B, C. And what are the coefficients of the vector of the image?
Also ABC.
No. It's not the identity function, right?
B2C and
Yeah. So what did you say, Sammy? I think you are correct.
if Thomas didn't, if no one heard me, then I'll let Thomas figure it out.
No, just say
Okay, B2C and 0.
Great. That was very condescending. Way to go.
No,
Okay.
no, no.
No,
I feel bad because like I hate it when like
I would give Thomas
and
a
then someone
chance
me answers
for
the
one.
question. No, no.
I'm sorry, Sammy. I'm just kidding.
I'm not.
It's
I'm
okay.
hurt.
But you got two answers correct straight, so you are allowed to condescend anyway. So it's B, 2C, and 0. Agreed?
Why in that order?
Uh, the short answer is it doesn't have to be specifically this order, but once you choose an order, you have to stick with it. But in general, it doesn't have to be in that order. Actually, it could be the coefficients which we will call coordinates depends on the basis we choose, and they could vary very much. And a large portion of linear algebra 2 will be dedicated to speak about coordinates in different bases and the repercussions of choosing a coordinate system. So it's a very big issue, to be honest. We will start in linear 1, but we will deal with it a lot in linear 2. But for now, let's leave these questions aside. That's the translation. Let's do it like the most natural way. And in the natural way, I read it from left to right. The constant, then the coefficient of x, then the coefficient of x squared. And I did the same here, right? B is the constant, 2c is the coefficient of x, and 0 is the coefficient of x squared. Agreed? So now it doesn't seem like such a big deal. What are the scalars here? The scalar here will be multiplied by a. Do we wish a to appear here?
No, because it's 0.
So the scalar will be 0, right? What would be this scalar here?
1,
Great. And that scalar here?
0,
0, great. Here, what is the scalar?
0,
And that one?
also 0,
And the third one?
2.
2. And the last row is 0,
Just
0, 0. So that is the matrix. So T is this matrix here. We will have an exact notation for it later, but for now, this matrix derives polynomials up to degree 2. And you could imagine that we can do it for every degree we wish. The next one would be 0, 0, 0, 3, and then 0, 0, 0, 4, and so forth. But yeah, and there is a matrix that derives the polynomial. Any questions so far? And the only thing we needed was the translation. How instead of a general vector, I take vectors of coefficients, and we will define it exactly in a while using the definition will be called coordinates. We'll do it in a while. Any questions up until now? Okay. An important example. I'll give only important example. An important example. Given a matrix A in a size m times n. Define the matrix function TA from Fn to Fm by TA of V is simply A times V. What that function does is multiplying the given vector by the matrix. Notice that the multiplication is defined because the size here, the number of columns is n, the number of rows here is n, and therefore the multiplication is defined. The output is of size m, so that defines a function. And proposition, the matrix function is linear, is a linear function. And the proof is quite easy. What is TA of V1 plus V2? What does the function does?
It's TV1 plus TV2, which is the same as the sum.
We need to prove, but what does it actually does?
It multiplies A times V1, and then it sums it.
V1 plus V2. Do you agree?
Yeah.
And now, due to distribution law, AV1 plus AV2, which is TV1 plus TV2. Similarly, TA of CV is A times CV, which is CAV, which is... Sammy, why do you keep going from place to place?
Do you really want to know the answer to that? First I was at Rami Levy, then I was coming back to the dorms, and I made myself lunch, and now I'm going to the library in the engineering facilities.
Oh, I see.
Because it's nice and air conditioned, and I don't have to pay for it.
No, I thought just that you were thrown from places. Okay, so it was a surprisingly good answer for that question as well. So it's C times AV, which is C times TA of V. Now I'm noticing that here I, by mistake, didn't write TA. That's the name of the function. So what we've proven here, while Sammy was getting his lunch, is, well, wrote it, I just said, the matrix function is a linear function. That means that every matrix is a linear function if you multiply by it. Right? And we still need to be convinced that every linear function is a matrix function, which means they are the same. Every matrix is a function, and every function is a matrix. Okay, so that's the more interesting part of the question. And the fact that every matrix is a function, linear function, we've just proved it in 2 seconds. Because the rules are matrix algebra, like Thomas said, that's less interesting. But it's surprising is that there is nothing else. Every linear function, not just this one that we found out by ourselves, must be multiplication by some matrix. And I always need to say if the vector spaces are finitely generated. By the way, if they are not finitely generated, the thing is that it's still a matrix, but the number of rows or columns is infinite. So we cannot really call it a matrix. So that's that. Any questions so far?
Right now, it seems like linear transformations are only for uh, for functions that only take the values of the original vector and doesn't sum any constant to it. Maybe I'm wrong, and I
Yeah, but
really
that's exactly matrix multiplication,
yeah.
right?
Okay.
It's the same thing because it's a constant time the first variable plus a constant time the first. It's a linear combination of the constant. Exactly. That's exactly what I'm claiming. But it needs to be proven. But it's exactly what I'm saying, and it's true. Okay.
Okay.
Just something I will write. Why are linear functions so important? Basically, because everything is linear. That seems a bit harsh. And if not, it is locally linear, meaning differentiable, right? We learned in calculus the differentiability is looking linear up close, right? So I'm exaggerating a bit because we do know there are non-differentiable functions, right? But most things are differentiable, and therefore are locally linear. And actually, in calculus, that you will not study, to be honest, but engineers and mathematicians do. When you do double integrals and triple integrals and differentiability of functions in high dimensions, you see that the derivative is the differential is actually a linear function represented by a matrix, and the chain rule in general is multiplication of matrices. Okay, that's I might be able to show you in Wikipedia chain rule. So I find it very interesting because being differentiable is being linear, and do they show it? That is so stupid. Can't believe it's in Wikipedia. Just a second. Just a second. No, come on, show me matrices. It is written here, but I wanted to actually show you a matrix, and it's not written here, sadly. It takes a bit of the wow factor here, sadly. But where I saw the, yeah, no, yeah, it doesn't show it. Too bad. But in any case, it's a multiplication of matrices, and we have matrices in calculus as well. That was my point. So these are linear functions. Linear functions are matrices, as we shall soon prove. And I wish to give you another example. Given a linear function t from R2 to R3, assume that T of 1, 2 is 1, 2, 3. And T of 1, 1 is 0, 0, 0. Could you calculate T of 0, 1? Could you calculate T of AB in general? Think of it before you answer, Thomas, just a second. From discrete mathematics point of view, it's ridiculous because there are infinitely many vectors in R2. I only told you the image of 2 out of the infinity, and I'm asking you to calculate everyone else. So if it was a general function, the answer will be obviously not. The fact that 1, 2 goes here says nothing about 0, 1. But because it's a linear transformation, it might be that you will be able to calculate these things. Okay? So now, Thomas, first, can you calculate T of 0, 1?
Yes,
How?
because we have T of 1, 2 and T of 1, 1, we can make the subtraction from T of 1, 2 and T of 1, 1 and get 0, 1.
Yeah. And think about it as distribution. Take T as so-called common factor, and it's allowed because that's the rule we know about linear transformations. The minus here does not cause any harm because it can go, it's a scalar that can go into the function. So it's T of 1, 2 minus 1, 1. Agreed? That's taking T as a common factor, which is allowed. And this is T of exactly 0, 1. But we know the values of these two. And therefore, T of 0, 1 is 1, 2, 3 minus 0, 0, 0, which is 1, 2, 3. Agreed? What about a general AB?
I'll let someone else answer.
How very big of you. Oh, okay. So,
No, I think yes, you can.
but can you tell me how? The
Yeah.
answer is you're right. But how do we get? Tell me your thoughts, and then I will rephrase
So
them.
basically, because we have already T of 0, 1 and T of 1, 1, we can subtract one from the other and get both T of 0, 1 and...
That's a great answer, to be honest. I didn't think that I'm pointing you in this direction, but I like that answer. So T of 0, 1 is 1, 2, 3. What is T of 1, 0? So we can say it's T of 1, 1 minus T of 0, 1. Do you agree about that?
Yeah.
Which is, what's T of 1, 1? That's 0, 0, 0. T of 0, 1 is 1, 2, 3. So that's minus 1, minus 2, minus 3, right? So now, how can we get T of AB out of the whole thing?
We sum AT10 plus B.
A of 0, 1, of 1, 0, plus B times 0, 1. And again, the point here that I will define, I'm showing you examples that follow the story I wish to tell you. The points are the coefficients. In the polynomial, the coefficients were trivial. because a polynomial is actually written by the coefficients, right? Here, well, so when you chose 1, 0, and 0, 1, the coefficients again were rather trivial because A is the first coefficient and B is the second coefficient. But we don't always have to go through what is called the trivial basis, the 0, 1, 1, 0. And I will show you an example. And I meant to show you an example now, but Thomas just went straight ahead to the trivial base. But I will show you afterwards another example when this is not the, I don't know, the fastest way to go about it. So in any case, the coefficients are the main thing here. It's A times T of 0, 1, 0 plus B times T of 0, 1. Both of them we know. So it's A times minus 1, minus 2, minus 3, plus B times 1, 2, 3, which is B minus A, 2B minus 2A, 3B minus 3A. So that is all together the function T of AB equals that. So we can write it in short as, I'm not sure in short would be helpful. And you can plug in the original vectors and check if you're not mistaken, right? If we plug in 1, 1, what do we get? What is T of 1, 1? It's indeed 0, 0, 0. And what is T of 1, 2? It is indeed 2 minus 1, which is 1, 4 minus 2, which is 2, 6 minus 3, which is 3, right? It's not a full proof, but it's good that it worked, okay? So now we'll take a break until 2:15, and then I will do another example from R cubed, which will be a bit more complicated from arithmetic's point of view. And then I will give the definition of what I'm talking about here in general. So have a nice break until 2:20. See ya. Hi, we're back. So, as I promised, we will do another example. Consider the linear transformation T from r cubed to r squared such that T of 1, 2, 3 is 1, 0, and T of 1, 1, 1 is 1, 1, and T of 0, 1, minus 1 is 2, 0, 2. Calculate T of A, B, C in general. So it's the same question, only with different numbers. And why here do we have 3 equations? And here we had only 2. What is the difference? Can anyone guess?
That we need linearly independent vectors to find solutions.
We need a base for the domain. The domain here is 2-dimensional, and the domain here is 3-dimensional. In order to know to where each vector goes, we need a whole base of the domain. So that's the main thing. And the idea is the same, just now it's harder to do in our heads. We might be able to follow up on Thomas' an idea of finding 1, 0, 0, 0, 1, 0, but that's not a scalable approach. We wish to find coefficients, and let's call them C1, C2, and C3, such that A, B, C, the general vector, will be created with the vectors that we are given. Okay, you see? We know what the function does to this vector, to that vector, and the third one. So we wish to create the vector ABC, a general vector ABC, using a linear combination of these 3. Why is it allowed? Just like we said a moment ago, because this is a basis. So it spans everything. So every ABC must be able to be created using these 3 vectors. So we want to find these C1, C2, and C3, which obviously will be dependent on A, B, and C. And then after we'll find them, we can apply the function T, and we get on the left-hand side T of ABC, and on the right-hand side, what will you get? What will you get? What's T of all of them? Yeah.
C1, T1, 2, 3, C2,
Exactly.
T1.
T of 1, 1, 1 plus C3, T of 0, 1 minus 1. But we know what are these equal to. will be C1 times 1, 0 plus C2 times 1, 1 plus C3 times 0, 2, which can succinctly be written as C1 plus C2, C2 plus 2 times C3. And that will be our answer. T of ABC will be equal to, a second, T of ABC will be equal to that object right here. Okay, but we need to find C1, C2, and C3, which I think right after this example, we will write them as a formal definition. C1, C2, and C3 are called the coordinates, right? They say, what distance should we go in every direction of the basis? Think of a basis of a number of x's. So these say what distance should we go on any axis in order to get to the specific vector, ABC. So C1, C2, and C3 will be called coordinates of the vector. And when you take different bases, you will get different coordinates for the same vector. And that's for later. Now we just want to solve this specific example. So how will we find C1, C2, and C3 from that equation? What should we do?
We know that whatever the first value is, it's C1 plus C2, and the second value.
Exactly. That's a linear set of equations, basically. So we know that C1 plus C2 equals A. And we know that 2 times C1 plus C2 plus C3 equals B. And we know that 3 times C1 plus C2 minus C3 equals C, where A, B, and C are parameters, and the variables we wish to find are C1, C2, C3, and we will obviously use a matrix to solve this system of equation. So
sorry, where did you get like the equations of all of them?
you said them yourself, right?
Yeah,
Why did you?
Yeah. No, I mean, because you have the first value being C1 plus C2, and the second value C2 plus 2C3.
2 times C1.
Oh, okay, yeah.
1 times C2, you see?
Mm-hmm. Yeah.
Okay. I think you were confused maybe with this, because that's the image already.
Yeah.
We're not there yet. We're just looking at the domain here. We just wish to represent or create ABC using the basis of the domain at this specific part. So we'll write a matrix. This is A, B, and C. And here the vectors will just appear in columns. That's the shorthand to go about it. And now we wish to solve it. So we wish to get to the reduced echelon form, and we'll do it rather quickly. So it's R2 minus 2 times R1, R3 minus 3 times R1. And so we have 1, 0, this minus 1, 1b minus 2a. Here we get 0, minus 2, c minus 3a. Next. R3 minus 2 times R2, which gives us 0 minus 3. And here, let's do it slowly. So it will be plus A minus 2B plus C. Hopefully I didn't make a calculation error, but I will be able to verify it by the end. And next, we'll fix the pivot elements, minus R2 and minus a third R3. And we get one minus 1, 2a minus b. And here we get 1 and minus a third of a plus 2/3 of b minus a third of c. And the last two operations will be one after the other. R2 plus R1, which gives us, and you see while I'm solving the problem, why is it important to be able to perform Gauss elimination and not get stuck with it, because it looks long and confusing, but it's just technical algorithm, basically, but one that needs to be done. So R1, R2 plus R3, sorry, I wrote R1 plus R3. So this is 0, and here, 2a plus minus a third is 5/3 of an a, minus b, that's a minus third of b, and minus a third of c. And lastly, above R1 minus R2, and we get to I didn't copy it. And we get to here, this is 0, and R1 minus R2. So that's minus 2/3 of an A plus a third of a B plus a third of a C. So it's not the prettiest answer, but hopefully it's a correct one. So what does the first equation tells us? What is the first row of the matrix? What is the equation behind it?
You mean minus 2/3 or?
No, I mean, what did we solve, right? We had the system of equations, right? First equation was C1 plus C2 equals A. That was 1, 1A. Now, after we got to the reduced form, what does this equation? C1 equals that, and C2 equals that, and C3 equals this. We found them. Okay, so C1 is a third times this monstrous thing, but taking a third out will help. minus 2a plus b plus c. C2 is a third times 5a minus b minus c. And C4, sorry, and C3 is a third times minus a plus 2b minus c. Let's verify these results. We wanted that A, B, C will equal C1 times 1, 2, 3 plus C2 times 1, 1, 1 plus C3 times, who remembers? 0, 1, minus 1. We found them all. Let's see if it's true. Let me be optimistic. Indeed, A, B, C. I won't write the A, B, C. A third times the C1 is a third times this times 1, 2, 3 plus a third, that's C2 times 1, 1, 1 plus a third times this is C3 times 0, 1, minus 1 equals, and now this is confusing because this sometimes look to students as a vector as well. But this is not a vector, this is a scalar. It's a complex formula for the scalar, but altogether it's a scalar. So we multiply it by all coordinates of the vector. And what do we get altogether? So let's take a third out as a common factor from everything. And what do we have? We are left with. So on the left coordinate, we get minus 2a plus b plus c plus 5a minus b minus c. And that's it. Why? Because this is 0. So on the left coordinate, when you multiply this by 0, you get 0. Only the first two coordinates did something here. What is the sum of everything here?
3a.
3a. Is it good that it is 3a?
Sure.
Because 3a over 3 is simply a. That is what we want, right? We want the sum to become ABC. Okay? The rest should be 3b and 3c. Sammy, do you have a question?
No, did it look like I had a question?
Yeah, because you did like this. Yes. Okay. Fine. So the next thing is multiplying by 2. Minus 4a plus 2b plus 2c plus 5a minus b minus c minus a plus 2b minus c. That's elegant. What are we left with here with? Let's look. Minus 4a plus 5a is a. Minus a, the a is canceled out. Next, 2b, or not 2b, sorry. 2b minus b is b, plus 2b, 3b, who would have thought? And lastly, 2c minus c minus c, dear Lord, it worked. Lastly, let's take the third one. It's minus 6a plus 3b plus 3c plus 5a minus b minus c plus a minus 2b plus c. And the last one No, that was horrible. Okay. And the last one is minus 6a plus 5a plus a is 0. 3b minus b minus 2b is 0. 3c minus c plus c, it's all together a third times 3a, 3b, 3c, which is a, b, c. It worked.
Very confusing.
Thank you. But I hope that, I think one of the reasons that students find this subject scary is because the calculations looks like this. But other than the numbers being horrible, the idea behind it is not that difficult. That's why I start with the easy questions where A and B could be found easily. But in general, to get to ABC using 1, 2, 3, 1, 1, 1, and 0, 1, minus 1, it takes ugly numbers, okay? And the answer for the question, remember, is this. And now I can plug in the C1, C2, and C3 that we found and get to the final answer. And we showed that T of A, B, C equals that, which is, and thus T of A, B, C equals, so what is C1 plus C2? So again, I will take a third as a common factor to make my life easier. So what's C1 plus C2? That's 3A, comma, and here C2 plus 2 times C3. So it's 5A minus 2A, that's 3A plus, minus B plus 4, that's plus 3B, and lastly, minus C plus 2 times, it's minus 2C, 3C, sorry, which is A, comma, A plus B minus C. So the final formula seems not that horrible. Let's verify this answer. And how do we do that? Our assumption was these three equations. Let's make sure that they are correct, that they follow the formula we found in general. So let's see. We claim the final answer is T of ABC equals, let's do it cyan. T of ABC equals A, comma, A plus B minus C. I'm surprised at how well the final answer got out. Let's see if it's correct. If I plug in 1, 2, 3. So first of all, we can...
Sorry, Aris, one question. You said it's T of ABC equals T of 1/3 of this, or? Oh.
No, not T of, just this.
Okay.
Because of this, and I'll remind you, where did this come from? We originally said if we'll find C1, C2, and C3, we will apply then. Now we're at the then. We'll apply T on both sides. On the left-hand side, you get T of ABC. On the right-hand side, you get C1, T of that, T of that, T of that. But these are vectors in R2. So you got this all together. Agreed? Tomas?
Yeah. Okay.
Okay. So if you plug in 1, 2, 3, what do we get? The A is 1, so this is 1, that's great. And then A plus B minus C. What's 1 plus 2 minus 3? 0, yay. Now plug in 1, 1, 1. What do you get here when you plug in 1, 1, 1?
1, 1.
Yeah, because the A is 1, these 3 are 1, so it's 1 plus 1 plus 1. 1, 1. Tomas, did you actually calculate it or just looked at the final answer and guessed it would work?
No, I thought about it and then realized that it was
Right.
also written down. So I said, okay,
Yeah,
well,
yeah.
I look dumb now.
Yeah. Yeah, but it's silly because I do wish for you to calculate it and make sure that's the verification we're doing. Lastly, if A is 0, B is 1, and C is minus 1, so we get 0 and 1 minus minus 1, it's 2. So yes, indeed, all these 3 equations hold this formula, and therefore it works in general. For every ABC you will put, that is the function we found. Any questions up until now? So here the calculations were difficult, but the idea is hopefully not too horrible. And you have to go over this material because it is imperative for linear algebra 2. In linear algebra 2, this whole thing is considered trivial. Okay? And so you have to trivialize it. The formal definition of part of what we did. Definition. And just a second. Internet connection. Oh, it's fine. Okay. Definition. Given an n-dimensional space V with an ordered basis V1, Vn. Okay, so we have why does the basis has to be ordered? Because we wish to find the coefficients. So in order to know which coefficient match which vector, there has to be an order. That's exactly like Thomas asked me, does it have to be in that given order? No, but it must be within some proper order that changed throughout the exercise. So we have a basis, an ordered basis, let's call it B. And then for every vector within the vector space, we define the coordinates noted by the coordinates of V according to B. We define them to be C1, 2, vertical dots, not center dots, B dots. C1 to Cn to be the coefficients of the basis, i.e., if we wish to get to V, we multiply the first vector by C1 and the last vector by Cn. I hope you realize that's exactly what I did before. I took an arbitrary vector and I wanted to find its coefficients according to the given basis. The basis there was 1, 2, 3, 1, 1, 1, 0, 1, minus 1. Okay? So the coordinates are the coefficients of the basis. Remember, the coordinates are the coefficients of the basis. That's the definition here. So we did all the calculation. Now we've just given it a name, and I'll write it as an example. And B is 1, 2, 3, 1, 1, 1, 0, 1, minus 1. We calculated that the coordinates of ABC are third time, and now the horrible values here. This is C1. That is C2. Lastly, this is, and we'll do a simpler calculation of it in a second, so you won't get scared by all the scary formulas. Before I move on, do you have any questions so far? Yes, Thomas.
I'm trying to think. So the process is the same for any sized matrix.
Yeah. Computer could calculate it. Yeah.
Okay.
The algorithm is easy. What's hard to do is keep it in your head and remember the connection between the coordinates and the actual vector. That's the hard part. Calculating it is easy, even though the result could be ugly. Let me give you a few examples. Say the basis B is 1, 1, 1, 2. What are the coordinates of 1, 1? So the coordinates are the coefficients. What are the coefficients of these two vectors that yields 1, 1? What scalars will you multiply the vectors of this basis that would yield 1, 1?
See, 1, 0.
Exactly. 1, 0. Because if we multiply this by 1, we already got 1, 1, and the rest is 0. Similarly, what are the coordinates of 1, 2 according to this base?
Also 0, 1.
But also it's 0, 1, right? This is 1, 0, this is 0, 1. Okay. What are the coordinates of 1, 3?
Um,
That's a bit more challenging. Do you agree?
yeah, it's 2 minus, no, minus 1, 2, right?
I have no idea. Let's calculate.
Okay.
Let's calculate it. We wish that 1, 3 would be C1 times 1, 1 plus C2 times 1, 2. So we get, again, a linear system of equations. What is the first equation?
Um, 1, 1, so C1, C2.
C1 plus C2. What is that supposed to equal to?
A.
But we didn't write an A in general, so 1, right? But
Okay.
you're correct that it would be preferable to do it in general with AB, and I will do it in a few seconds. But first of all, I'm simply solving the specific vector. And what is the second equation?
C1 plus 2C2.
Plus 2C2 equals 3. And now we can solve it. And we get here 1, 1, 1, 1, 2, 3. And let's solve it quickly without writing the steps. The second row minus the first row. It's this. And lastly, I think you are correct, Thomas, right? It's minus 1, 2. That's what you said. Let's write this is C1, C2. These are the coefficients. And indeed, let's use the coloring. C1, C2, color them green. C1, C2, color them green. The coordinates are the coefficients of the bases. So 1, 3, B equals, the coordinates are minus 1, 2. Any questions so far? Let's calculate the coordinates here in general. In general, if the coordinates of AB are C1, C2, then you get, we jump to the matrix, then we get AB here. And then 0, 1, B minus A. And lastly, first row minus second row, so that's 0. And here you get 2A minus B. So the coordinates are 2A minus B, B minus A. Let me see something for a second. Yes. Okay. Remember this example? So Thomas solved it by a trick. Now we can do it again without a trick using the coordinates we just found. So let's go back to the example, this example. And then we say, what is T? Find T of AB. Okay, that's the question. So what am I claiming? And I'll ask of you to try to tell me. What does AB equal to? What does this tell us? What do you do with the coordinates?
So each coordinate is to like 2CA, 2C1 minus the C2 equals A, or that's not how it works.
No, I don't think so. The coordinate, this whole thing is C1. That's the first coefficient. So we multiply it by which vector? The first vector, right? Because the basis here, to be honest, it's the second vector. The basis here is 1, 1, 1, 2. C1 is multiplied by 1, 1. C2 is multiplied by 1, 2. We found that C1 is 2A minus B. So that is multiplied by the first vector plus B minus A multiplied by 1, 2, the second vector. So this, cannot write it enough times. Wait a second, I cannot even write it one time. So this thing over here translates exactly to that. The coordinates are the coefficients of the bases. Okay, agreed? So what is the next step if we want to find T of AB? What do we do?
Do we distribute?
Before, yes, but before we need to apply T. Agreed? So you get T of AB on the left-hand side. And on the right-hand side, what do you get?
One, two, 3 times
That's
2A.
Kaur, exactly.
No,
Exactly.
0, not 1, 2, 3, sorry.
You're correct. You're correct. 0, 0, 0 plus B minus A times 1, 2, 3. And that is B minus A times 1, 2, 3. And if you remember, that is exactly the result we found before using Thomas's trick. Let's go back to this question. Here. Not here. No. Here. See, B minus A times 1, 2, 3. So the trick was nice, but it is not scalable to find tricks. The solution I've shown you works for any old base. Any question thus far? Okay. And I'm thinking with myself where to go on with it, whether to show more examples. I'll show another example, at least one example. say your basis is 1, 2, 3, 1, 1, 1, 0, 1, minus 1. Okay. This question will not be complex, even though I use the same basis. Assume that the coordinates of some vector b are 1, 2, 0. Find the vector v. So here we go the other way around. Instead of giving you a vector and asking about its coordinates, this time you are given the coordinates and you are asked, what is the vector? This is the easy part of easy direction of the implication. Why? And that's the main thing you need to remember. When given coordinates, what do you do with the coordinates?
You multiply each one by its corresponding vector.
In there, just finish the sentence. In the basis, exactly.
Yeah, that's
Yeah. So for short, I say we multiply by the basis. What do we do with coordinates? We multiply by the basis. Okay. In Hebrew, it's a bit more succinct than כופלים באיברי הבסיס. You multiply in the basis elements. Okay, maybe that's better. But in any case, exactly as Sammy said, these are the coefficients of the bases. So V is 1 time 1, 2, 3 plus 2 times 1, 1, 1, which is altogether 3, 4, 5. Let's verify that. Verification. We found the general formula for the coordinates in this case. That's the general horrible formula. Let's plug in 1 to 0, and hopefully we'll get the same 3, 4, 5, right? So what's I was mistaken. Let's look at the coordinates of 3, 4, 5, and hopefully there's supposed to be 1, 2, 0. So let's try. -6 plus 4 is -2, plus 5 is 3 over 3. That's 1. Next. 5 times 3 is 15, minus 4 is 11, minus 5 is 6, over 3, that's 2. We're 2 for 2. Lastly, -3 plus 8 is -5, is 5, sorry, -5, 0, 3 for 3. Okay, you see? So given the coordinates, finding the vector is easier. Even the vector, finding the coordinates, it's not really tough, but it requires some calculations. Any questions so far up until now? Okay. So now I'm ready to give you a theorem. I will do a short introduction behind it. I don't have time to prove the theorem, but it's imperative that you know what it says. So, short story, and then a theorem. So what is the short story? We have some vector space V, which is sent by a linear function t to a space W. We wish, instead of a function, what do we wish to substitute instead of linear functions? What is the main purpose?
Can you ask the question again?
I wish to substitute the function t with something. What is the replacement
A matrix?
of exactly a matrix? So I want this to be a matrix. Okay. What will I multiply the matrix with?
V.
But what is V? What type of vector it is?
Any.
It's right? It's n. It's not what it said. It's a sequence of n coordinates, right? That's like we did with the polynomials here. When we wanted to find a matrix which derives the polynomials, we said we cannot multiply a matrix by a polynomial, but we are able to multiply a matrix by a column, right? So that's what we want. Instead of vectors, take a column. And maybe M is the better word. The letter here doesn't matter. To Fn. And what would be the transformation here? How do we get, to be honest, it's two-way transformation. And let's go to arrows. What would be the connection here? So a matrix will bring me from here to here. But how do I make the journey from a vector to a set of coefficients? What would that be?
Do what we just did just now?
Yeah, that's the coordinates, exactly that. That's the coordinates, okay? We use the coordinates to transform vectors into a sequence of coefficients, which we can multiply by a matrix instead of applying the function. So we wanted to apply the function t. Instead, we multiply by some matrix that does exactly what t does, just translated to the coordinates. So if we know that tv equals w, say the matrix is noted by this. This is a matrix. What will we multiply it by? We cannot multiply this matrix by the vector v, right? Because we cannot multiply a general matrix by a general vector. But what can we multiply the matrix by? Not the vector itself, but
is it Just coefficients from the field.
Yeah, the coordinates, exactly. And how do we note the coordinates of V?
The square brackets.
Exactly, square brackets, and I write the base here, right? And what do I expect the result to be? It won't be the actual vector W, but its coordinates by some base of the range. And we write the bases B and C here. So that is the representing matrix of the linear transformation. And now I'll write it up as a theorem. Given two finitely generated vector spaces, given two finitely generated vector spaces V and W over the same field F, and given B and C ordered bases for V and W respectively, and assume that the dimension of V is M and the dimension of W is N, then there exists a unique matrix which we denote by the representing matrix of T from B to C, such that for all vectors in the domain, it is true that when you multiply by the representing matrix the coordinates of a general vector, what do you get? Who can finish this formula? I took the
WB.
yeah. So WC is good, but what is W? I didn't use the name W. Could you refer to W without using W, just using the letters written here? And
F of
to be
N.
honest, I forgot something else. I didn't mention the linear transformation itself. And given a linear transformation D from V to W. Okay. So what is it here you were starting to say?
Sammy?
Yeah.
What?
It's W.
Yeah, but we, like I said, we can't use the word W, the letter W, because it's not defined here.
It's DB.
Exactly. It's T of V, which is W, right? It's the same thing. But beforehand, I told you, let's write TV equals W, and then I use W. So in general, I don't need to take this extra step. I'm saying multiplying the coordinates of V by this matrix, we get the coordinates of T of V, which means here we have matrix multiplication, and on the right-hand side, we applied the function t. This is not multiplication, this is the application of a function. So that's the theorem that says that every linear transformation is actually a matrix. Only we need to work with the coordinates in order to do so. And in linear 2, we learn how to find a basis such that the matrix is nicer. What is nicer? Usually diagonal. And I will give you an example in a short while. Any questions so far?
Yeah, I'm not really understanding this that much.
I'm not understanding what's the difference from what we were seeing until now to turn it into a matrix.
No difference. That's what we did throughout the entire day today, the entire session. I just given everything names. I said, instead of just saying coefficients, I said they are called coordinates, right? And the matrix that matches T is the representing matrix of the linear transformation. Where do I have such an example? It was a long time here. So now I would write T within square brackets, and I say that's the matrix. So it's no different. I just use the terminology, the correct terminology to write all this stuff accurately. But it's not new. That's exactly what I've been saying all along.
I don't understand why you didn't want to use W in the...
Because it means nothing. You cannot use a letter that means nothing. Small w is not a letter here, right?
But small v isn't a
Small
letter
v,
either.
no, but it is, because I said for each vector v, the multiplication is, and if I write here w, it's meaningless because I don't know who w is. But I know it has to be t of v, right? And that's what you assume W is anyway. Do you agree, Sammy? The W was the image of V, the vector that V is sent to?
Yeah.
So that's just saying here W means nothing. It's like using a variable that you just declared and didn't put anything in, right?
Right. So this is the same as saying T is V to W.
Yeah, and that's what I said here. Here I wrote before, let's call TVW, and then yes, I said that V goes to W. Agreed? It's the same thing, just written differently. Let's try an example. Wonder if I'm able to run through it. No. I have only 5 minutes and I feel that we had enough. You need to digest this stuff. And next week, we will start from this point. Okay. And then what was the number of lecture? $13. So the next lecture is 13, final one. So lecture 13, we will start with an example for finding and the representing matrix of linear transformation. And in order for you to be able to do homework, I'll give you the assumptions now, and you can try to calculate it by yourself, and I will do it together also next time. So T will be from R squared to R cubed. The formula would be T of xy equals x plus y, y. The basis will be, the first basis will be 1, 1, 1, 2. The basis for the range would be 1, 1, 1. I'll do something not as complicated. 0, 1, 1, and 0, 1, minus 1. Okay? So try to do it by yourself, but we'll do it together next time. Find the representing matrix of T from B to C. You want a matrix that does this operation here using the coefficients according to these horrible bases here. And the ability to do it is very important, not only for this course, but for the next course afterwards. And with that, I bid you adieu, and I'll see you guys at 4 for calculus. See you later, alligators. Saving the PDF file.